All right, this lecture is on the t-test for dependent means. Last lecture, we learned about a single sample t-test or a one sample t-test. The one sample t-test is an alternative null hypothesis significance test, so the z-test, and we use a one sample t-test when the population variance is unknown. And therefore, we have to estimate the population variance based on the the variance that we calculate in our sample. So in order to do a one sample t-test, we still need to know a population mean, or we need to have a logical comparison value that we can use for mu, for example, the midpoint or a neutral point of a response scale on a survey or questionnaire. In the previous lecture, we gave an example of having a logical comparison value based on picking the neutral point from a response scale about students' attitudes towards drinking. There's another similar example about using the midpoint of a response scale as a logical comparison value. And you can find that in the textbook on page 235. There's an example about people's feelings of hopelessness after a flood. I wanted to show this graphic from the textbook because I think this graphic and similar graphics that the textbook uses are really great ways to understand null hypothesis significance testing. And so there's several of these that are presented in chapter 5 and chapter 7. And so if you kind of understand what's happening with these diagrams, you'll have a really good handle on null hypothesis significance testing. In particular, what I've found to be one of the hardest concepts for students is to understand this middle part of the diagram, which is what a comparison distribution is. And for our z-tests as well as our t-tests, our comparison distribution is a distribution of means. Okay? Another word for this is the sampling distribution of the mean. So the sampling distribution of mean, otherwise known as a distribution of means, was the focus of lecture 7. And if this concept is still a bit fuzzy for you, I highly recommend to go back to that lecture as well as to review the textbook for what it conceptually means to have a distribution of means. So we're going to be seeing diagrams like this quite a bit more in subsequent lectures, so it's, I think, really important to get a handle on what these diagrams mean. All right, so now we're going to move on to the t-test for dependent means. And this is another type of a t-test, and it really builds on what we've already learned regarding a one sample t-test. So it's kind of an extension of that. So if you understand the one sample t-test, you can understand how to do a t-test for dependent means. A t-test for dependent means is important because many important research situations involve collecting 2 scores from each person in your sample. So whereas with a one sample t-test, we just had 1 score from each participant. But here we're going to have 2 scores from each person. So this is often done in repeated measures designs. And another name for repeated measures design is a within subjects design. And what happens is the same measurement is collected from the same person at 2 different points in time. So for example, we might measure a person's sense of well-being before and after meditation. Or we might want to measure practice scores on an SAT before and after participants take an SAT prep class. So repeated measures designs are used to assess change, improvement, or a reduction. So these are very common designs in social and behavioral sciences, and we analyze these types of designs with a t-test for dependent means. All right, so we use a t-test for dependent means where this allows us to do a hypothesis testing procedure in which there are 2 scores for each person, or pair, and the population variance is unknown. So just like a one sample t-test, the population variance is unknown. What this test is going to do is test the hypothesis that there is a difference or a change between pairs of scores. So the process is very much the same as a t-test for a single sample. However, we're just going to use difference scores or change scores as our scores. So essentially what we're going to do is we're going to take a participant's post score minus their pre-score and see what the difference is, okay? And then we're going to do that for everybody, and then we'll use the change scores as our data. Okay? Another way to think about this would be to say we've got participants that are in an experiment, and we want to see how they score after some experimental manipulation or treatment, and take the difference between their after score and their before manipulation score. With a t-test for dependent means, we're always going to assume that the null population, or comparison population, has a mean of 0. Okay? So really this null hypothesis would be whatever treatment we're giving to participants, whatever intervention, or perhaps we're giving them some sort of a drug or a substance. The null hypothesis is that there's no effect of any kind, no effect of the treatment, no effect of the drug, and therefore we see no change in people's score from before they had the treatment to after, or before they took the drug to after, right? So that you can think of the change score for each person as being 0. They have the exact same score at time 1 as they do at time 2. No change. That's the null hypothesis. Okay? So the null hypothesis is that there's no difference on average. All right. Now, what we should kind of have in our mind is that the null hypothesis is really about what happens on average. So it could be the case that, and this is often the case, that when you measure something on 2 different occasions, sometimes you get slightly different measurements. So there's reason to believe that every single person's change score won't be exactly 0. Okay? For instance, if you asked somebody about their sense of well-being, and we asked them today, and then we'd ask them 2 days from now, their sense of well-being is likely to be similar, but maybe not exactly the same. So even if nothing significant happens, we're likely to see some small fluctuation. But with the null hypothesis, we're saying that on average, the average amount of change should be 0. So maybe some people, their sense of well-being goes up a little bit. Maybe some people it goes down. Maybe some people it stays exactly the same. But on average, we're saying there should be no change or no difference on average. All right. And this is where it gets a little bit more technical, but what we're actually going to test with our t-test for dependent means is the probability that we get a sample of different scores, and that is a random sample from a population of different scores with a mean of 0. Okay, so it's a similar idea. With a one sample t-test, we're taking a single sample, we're going to calculate the mean, and we're going to say, is that sample mean different from the known population mean? Here we're saying we're going to take a sample of different scores, and we're going to see whether that sample of different scores has a mean that is different than the population mean of 0 under the null hypothesis. So let's do a concrete example to illustrate this test. So let's just say, for example, we're researchers that create an intervention to decrease depression, and we do this by prescribing 20 minutes of exercise per day. We measure depressed mood using a 0 to 10 scale for self-reported depressed mood, where small numbers mean less depression and higher numbers mean more depression. And we're just going to do a very simple study, which is often called a pilot study in research, and it's only going to have 4 people. And we're going to collect pre-scores and post-scores. So pre-scores refer to people's depression before the exercise intervention, and their post-scores refer to their self-reported depressed mood after the exercise intervention. So a pre and post repeated measures design. All right, so here's our first person. Before the exercise intervention, they reported a depressed mood of 9. So that's a high level of depression. And then afterwards, they reported a 2. So less depression. Our second person was a 10. And then they reported a 4. So they showed a reduction. Person number 3 was an 8 in depression. And so their depression actually went up by 1 point after the exercise intervention. And then our fourth person was a 9, and then their depression was reduced to a 1. So our question is, based on these 4 people, would we be able to conclude that our intervention worked at reducing depression? And not just among these 4 people, but could we say that it would work at a population level? All right, so we're just going to use our same 5 steps of hypothesis testing that we've already learned. And the first step is to restate the problem as a hypothesis about populations. Population 1 will be depressed people who exercise 20 minutes a day. That is, those people that participated in the intervention. Population 2 would be depressed people who do not exercise 20 minutes a day. Okay. Now notice that this is similar to imagining what would happen if depressed people don't participate in the intervention. Same thing. Our research hypothesis is that depressed people who exercise will show a reduction in depression compared to depressed people who don't exercise. In other words, we can say that the population mean will be less than 0. Okay, what are we really saying there? We're saying that on average, there will be a reduction in depression. So the average change score should be less than 0. All right. The null hypothesis would be that depressed people who exercise do not show a reduction in depression compared to people who don't exercise. So there we're saying that the average change should be greater than or equal to 0. Okay, so no change, no reduction in depression, okay, would be a change of 0, or then even worse, there could be an increase in depression. So if those scores go up, we'd have a positive change scores. So on average, we get numbers that are greater than 0. That would be if the exercise backfired and it led people to become even more depressed. Step number 2 is to determine the characteristics of our comparison distribution. All right, so under the null hypothesis, for a t-test for dependent means, we're always going to hypothesize under the null that on average, whatever we're trying to do, whatever treatment, whatever intervention is going to have no effect. And so that means 0 change. So on average, the population mean in the comparison population, the population associated with the null hypothesis, that average is always going to be 0. And if that's true, then we know that the mean of the distribution of means will also be 0, following rule 1 that comes from the central limit theorem. All right. Now, again, we don't know what the population variance is. And so similar to a one-sample t-test, we need to figure out the population variance so that we can figure out the standard error of the mean, the standard error. So we need to estimate population variance from our sample variance that comes from our treatment group. Okay, so we have this sample of 4 people, we have their data. If we figure out what the variance is in this sample, we can use that as an estimate of population variance. Okay. So our estimated population variance, S2, which we're going to substitute for sigma squared, will then give us the ability to determine the standard error of the mean. That's because we can use Rule 2a and figure out the standard error of the mean from our estimate of population variance. Okay. So what we're going to do is we're going to take our data. We've got pre-scores and post-scores. And for each one of our 4 participants, we're going to calculate a different score. We do this by subtracting the pre-score from the post-score. Okay? And this is the way that we're always going to subtract. This is the way that we're always going to create different scores, is by taking the pre-score and subtracting the pre-score from the post-score. Okay, so we've got 2 minus 9 to get a different score, otherwise known as a change score, of -7. We're going to take 4 minus 10 and get a different score of -6, 9 minus 8 and get a different score of 1, and then 1 minus 9 and get a different score of 8. It's important to subtract the pre-scores from the post-scores so that you can see the direction of the effect. So here, we can see from the numbers that there's a reduction. We went down 7 points. And so by making sure to subtract in a consistent way, subtracting post minus pre, okay, or subtracting the pre from the post, however it makes sense in your brain to think about that, we're going to capture that the difference was a reduction, okay? So always when you're doing those subtractions, take a look at your different scores and then take a look at your original pre and post and say, hey, does that make sense? Does that -7 make sense? And in this case it does, because what happened? There was a reduction in 7 points from pre to post because of the exercise intervention. All right. So that's how we calculate different scores. We're always going to do it in that same way. Okay. The next thing that we can do is figure out what is the average difference score. So all I did was take the sum of these numbers. Okay. So -7 and -6 is -13. Add a 1 to that, we get a -12. Subtract 8, we get -20. -20 divided by 4 is -5. So what we can see is that the average change was -5. There was an average reduction in depression of 5 points. So what we're going to do now is we're going to treat the different scores as our data. And then once we do that, once we've got our different scores as well as the mean, we're just going to follow all of our same procedures for doing a one sample t-test, just like we learned in the last lecture. So basically, the pre and the post go away, and we can just think of our different scores as our data. And then this just becomes a one sample t-test. All right. So what do we need to do next? Well, we know that we need to come up with a calculation of sample variance in order to use that sample variance as an estimate of population variance, so then we can ultimately figure out what our standard error is. Okay. So we figure out our variance using the same mathematical procedure that we've been doing, by taking the deviations from the mean, squaring those deviations, summing those deviations, and then dividing. Okay. So again, here too, we have to make sure that we're taking, we're doing our mathematical operations in the correct way. So we're taking this different score of -7, we're subtracting a -5. Subtracting a -5 is the same as adding a 5. So we get a deviation from the mean of -2. -6 deviates from the mean by -1. 1 deviates from the mean. That should be positive 6, beg your pardon. That's incorrect. Typo. That should be a positive 6. And then we've got negative 8 deviates from negative 5 by negative 3. All right. So then we're going to square those deviations. And then we are going to sum the deviations. So we're just calculating variance in the same way that we've always calculated variance. Okay. So we're taking the sum of the square deviations. And then just to illustrate, if we want, we can calculate sample variance as well as sample standard deviation in the way that we originally learned, which is just to divide by n. Okay, and that would be a good old descriptive statistic, just like we learned in the first week or weeks of the class. But the new thing that we learned that we need to do last lecture when we learned about t-tests is to come up with an estimate of population variance that isn't based on dividing by n, but is based on dividing by degrees of freedom, which is n minus 1. So what we're going to do is we're going to come up with our estimate of population variance that is based on degrees of freedom, which is, in this case, dividing by 3. 4 minus 1 is 3. Okay. And again, just to reinforce why we do this, is if we use our we can say uncorrected sample variance as our estimate of population variance, that number will be too small. If we divide by n and we just use our good old descriptive statistic, it's been mathematically shown that that number will consistently underestimate the true amount of variance that is in the population. So we just correct that number by dividing by n minus 1, and you can see that the effect is to have a larger number. So this larger number is thought to be more accurate. It's thought to be more representative of what the population variance truly is. So this is the number that we're going to use as our estimate of population variance. There we go. Okay. And right, recall that we have to divide by degrees of freedom instead of n so that we don't underestimate. All right, so in determining the characteristics of our comparison distribution, let's just lay out some of the numbers that we've got so far. Here's all of our descriptive statistics. Our sample mean was negative 5, so there was on average a reduction in depression of 5 points. Sample variance, sample standard deviation. Our comparison population, not our comparison distribution, but our comparison population, under the null hypothesis, would have an average change of 0 with a variance of 16.67, which is just our way of correcting the variance in order to have an estimate of population variance. Notice the notation, not SD squared, but S squared. Okay, this is instead of having sigma squared, we're going to use that S squared as our estimate of population variance. Okay. Our comparison distribution is a distribution of means. Because of rule 1, we know that that distribution of means will have a mean that is centered around 0, the same as the population. And now we just need to figure out what is the variance and the standard deviation of that distribution of means. We figure out the variance and the standard deviation of the distribution of means in the same way that we've already learned, rule 2a and rule 2b. So rule 2a, we get the variance of the distribution of means by taking the variance in the population divided by n. Okay, notice that n is 4 here. Again, we don't have to worry about that n minus 1 correction. We've already done. It's in place. It's been taken care of. Right? So we just use n here as our sample size. So we get an estimated variance of the distribution of means. We get our standard error by taking the square root of the variance of the distribution of means. Okay, so we were able to get then that our standard error is 2.04, and by way of interpretation, what that means is that any mean that we could possibly sample is likely to differ from the expected mean of 0 by 2.04 points. Okay, 2.04 points would be one standard error or one standard deviation in this distribution of means. Step 3, we're going to determine our cutoff for rejecting the null hypothesis. We have to do this using our t-table. And to use a t-table, we need 3 pieces of information. We need degrees of freedom, we need an alpha level, and then we need to decide whether we're going to do a one-tail or a two-tail test. Okay? So we know we have degrees of freedom, which is 3, because there was 4 people in our sample. 4 minus 1 is 3. Alpha level 0.05. Unless otherwise specified, by default, we're always going to use an alpha of 0.05. And then in this case, we're using a one-tail test. Why? Because we had a directional hypothesis. We hypothesized that the exercise program would reduce depression. So going to our t-table, one-tail test, alpha 0.05, 3 degrees of freedom, we've got a critical value of 2.353. All right, now what we have to ask ourselves is, do we want to have a positive 2.353 or a negative 2.353? Okay, what's the predicted direction of our effect? Is it positive or is it negative? Think about it for a minute and think about whether we should specify to have a positive 2.353 or a negative 2.353. Hopefully you chose negative 2.353 because we're specifying a reduction. Okay? We're expecting that our exercise program should reduce depression. Therefore, on average, we're going to see change scores that are negative. Therefore, we should be looking at on the negative end of our comparison distribution. So we want to have a negative critical value. Step 4 is to figure our sample score on the comparison distribution. Same as before, but now we're just, instead of doing a z-score, we're going to do a t-score. Okay. So -5 was our sample mean. We're going to subtract 0, which was the population mean under the null hypothesis, and then divide by the standard error that we calculated. That simplifies to t is -5 over 2.04, which gives us a t of -2.45. So now we're going to decide whether to reject the null hypothesis. Our critical cutoff score was -2.35. Our t is -2.45. Therefore, what should we do? Should we reject the null hypothesis, or should we fail to reject the null hypothesis? And think about it. We've got a t that is exceeding the critical value in the expected direction. Okay, therefore, we're going to reject our null hypothesis. Okay, so what we've got here, just to kind of go back to the diagrams, we've got at the population level, this is our population of individuals. This is what would happen if exercise had no effect. And so what we see is everybody in the population, their individual change score. Okay, we know that just randomly, some people might report a little bit more depression, some people might report less, but most people, if the exercise has no effect, they should be fairly consistent from time 1 to time 2. Okay, so on average, no change. And we figured out that the variance should be, of those scores, should be 16.67. Our comparison distribution is a distribution of means. This would be what would occur over the long run if we did this random sampling process over and over and over again. We're going to get a pile of means that is centered around 0, and that is going to have a standard error of 2.04. So now what we're doing with our sample data is we're trying to locate where does our particular mean fall in this comparison distribution. And what you can see is that it falls in the tail of this distribution. We had set up that the tail would be at -2.35. We got a t that is -2.45, so it falls in the critical region. And by the way, these have 2 little critical regions set up there, but we were doing a one-tail test, so maybe I need to update my diagrams. But anyway, So that's what we're trying to do. We're trying to locate our sample mean in this comparison distribution. Okay, so we would reject the null hypothesis and conclude that indeed our exercise program reduces depression. All right, let's do another example. And this is in the book, so you can follow along here and then also go back and read it in the book for extra reinforcement. What the authors of the textbook report is that there was a 2005 study in which the researchers examined neural activation in the brain, specifically in a brain structure called the VTA that is involved in reward. And so basically this part of your brain becomes active when people take cocaine or when they win the lottery. And so they hypothesized that being in love ought to activate this part of the brain as well. Okay, so they had 10 people in their study who were madly in love with their partner. So they measured brain activity when these people viewed a picture of their beloved versus some neutral person. And they wanted to know, would there be greater activation in reward-related brain regions when we see our beloved compared to when we see a neutral person? Okay, so to restate the promise hypotheses about populations, population 1 would be people who are madly in love. Population 2, people who are not madly in love, which would mean that they'd have the same brain activation when looking at either picture. The alternative hypothesis is that people who see a picture of their beloved will show greater brain activation relative to seeing a neutral picture compared to people who don't see a picture of their beloved. So in other words, their brain activation will be greater, that they should show a positive change. So their change scores on average will be positive or greater than 0. The null hypothesis is that people who see a picture of their beloved will not show greater brain activation relative to seeing a neutral picture compared to people who don't see a picture of their beloved. So in other words, seeing a picture of their beloved won't result in a change in brain activity, or it would show reduced brain activity compared to a neutral picture. So the pattern would be that change scores would be negative, would be close to 0 or negative if the null hypothesis is correct. Characteristics of the comparison distribution. We know that the comparison distribution, which is a distribution of means, will have a mean of 0. We don't know the population variance, so we need to figure that out. So the population variance needs to be estimated from sample variance, and doing so will give us the ability to determine standard error using Rule 2a. Okay, so here's the data. This is also reported in the text. What you can see, the numbers here reflect brain activation, and so we can interpret larger numbers as reflecting more brain activation. So here's the 10 participants, and the difference score is calculated as the difference between viewing a picture of their beloved minus neutral. Okay, and this is to reflect, here it's being done to reflect the difference between what happens when you see the one's beloved. So in this way, the difference is captured so that we can interpret the numbers as reflecting a change towards seeing a picture of their beloved from neutral. Okay. So I kind of wish I would have flipped the columns here to have it consistent with the other example, but the idea is to have the different scores reflect what happens when we move from seeing neutral to beloved. Okay, and we can see here that there's a positive change from neutral to beloved of positive 6. Here there's a positive change when we go from neutral to beloved. So kind of the short of it is the way that we calculate the numbers should be interpretable based on the phenomenon or the hypothesis. Okay? So when collecting those different scores, it's possible to then calculate the mean. And then we're going to use our different scores as our set of data. From these different scores, calculate our deviations and our square deviations to get sum of squares. And then from sum of squares, we're going to divide by degrees of freedom in order to get an estimate of population variance. From our estimate of population variance, we figure out the variance of the distribution of means, and then from that we can get the standard deviation, otherwise known as the standard error, and that will become the denominator of our T formula. To determine the cutoff for rejecting the null hypothesis, we've got our three pieces of information: degrees of freedom, alpha level, and we're going to do a one-tailed test because we had a directional hypothesis. Looking up in our t-table, we get a value of 1.833, and the key here is to say what side of the distribution should we be looking at. We predicted an increase in brain activation and constructed those different scores to reflect that there should be an increase as we move from neutral to beloved. Okay, so we're going to use a positive critical value, a positive 1.833. All right. Oh, sorry, typo there. It should say one-tailed test. So alpha with degrees of freedom 9, alpha 0.05. Please ignore what's typed here and listen to the words. A one-tailed test, the critical value should be 1.833. Calculating our t-score, we get a t of 5.58. Okay, as we can see, that greatly exceeds our critical value or our cutoff score. Therefore, we're going to reject the null. People who see a picture of their beloved do show, not will show, but do show greater brain activation relative to seeing a neutral picture compared to people that don't see a picture of their beloved. Okay. Here's the diagram. This comes from the chapter, but I wanted to put it right here. Again, just to see what all the diagrams mean. We've got a comparison population under the null hypothesis. This is what would be likely to happen if the seeing a picture of one's beloved had no effect. Okay, so imagining what would happen if there's no effect. Then imagining what would happen if we took all possible random samples of size 20, because there was 20 people in the study. Okay, so that random sampling process would produce a pile of means, most of which also had a mean of 0, but you could see that there'd be some variability there. And then we take a look at our sample data, the people that actually were in the study, and you can see that our sample data doesn't fall anywhere close to the comparison distribution that would happen under the null hypothesis. Okay. So here it's very evident and very easy to see why we would reject the null hypothesis, because our sample data doesn't resemble at all what is likely to happen if the null hypothesis is true. So it's very clear with these diagrams to see that we're going to reject the null hypothesis. Sorry, another slight typo there. That should be 5.58. All right. So 2 examples. And so just work through those. You can work through those examples again. It's the same 5 steps of hypothesis testing. The only change is that we have 2 scores from participants, but all we do is create different scores or change scores and then treat those change scores as our data. A t-test for dependent means goes by several different names. So another name is a paired samples t-test, also a t-test for correlated means, a t-test for matched samples, or a t-test for matched pairs. It's all the same. It basically means that we've got 2 scores, and these scores are related in some way. They can be related because they come from the same person, or they could be related because each score comes from one member of a pair or a dyad. So for example, psychologists that do research with a married couple would get one score from one spouse, one score from the other, and those scores are matched or linked together. And so then it's possible to treat them in very much the same way as with our examples here. All right. So in our previous examples, the scores are dependent or related because they come from the same person, but just like my example with doing research with married couples reveals, you can also perform this test with scores from pairs of participants by considering that each pair as if it were one person. Okay, so you can do this with siblings or a married couple, or even in educational research, you could look at two different classrooms and pair people up. So as different examples of an application for a t-test with dependent means, one research question might be, do wives consistently do more housework than their husbands? Okay, get a measure of how much housework the wife does, how much housework the husband does, calculate the difference between the two. That becomes a difference score. And you could look at that difference score across several different pairs of husbands and wives. Another example of a research question might be, do two members of a dyad have different task satisfaction depending on their assigned role? So for instance, we have two people work together. One is assigned to be the leader, the other is assigned to be the follower. Ask them what their task satisfaction is and calculate the difference. And then you could do that across multiple dyads. So these would be a couple different applications in research studies. This is from the chapter, but this is something that in reading published research is a place that you might encounter the results of a t-test for dependent means. What's being reported here are fathers' mean psychological states, as average psychological states, in the job and at home. And so these fathers completed a survey or a questionnaire in which they're reporting on these dimensions, the extent to which they are feeling important, or how much attention they're paying to whatever they're doing, the challenge that they're facing. Here's the range on that particular scale, as in scores could range from 0 to 9. And then what we see reported are averages. Okay. So the difference here is that in the work setting, on average, these fathers are reporting an average of 5.98, but here they're reporting an average of 5.06. And then what's reported in this column is the t-score. Right? It says, note that column 3 are t-scores, degrees of freedom 90 for all t-tests. All right, why degrees of freedom 90? It's likely they had some missing data. That's why it's 90, not 91. So there we go. You'll also see that we have these star symbols, okay, and we can interpret those stars as meaning that the test is statistically significant at either the 0.01 level or the 0.001 level. So these tests met a significance level that was even more significant than the conventional level of 0.05. Okay. So essentially, when you're reading research, we just have to kind of be familiar with the types of tests that are available to these researchers. Then we'll see a table of data and kind of have to say in our brains, oh, okay, these means were compared using a dependent samples t-test. Here's the t-statistic. They're telling me that it's statistically significant. So in the background, we don't know what the null, they don't report the null hypothesis. That's all in the background. You don't see a critical value. You just kind of see the end result or the end reporting. So as statistics students, we learn about the whole process, and then when it comes to reading research, we kind of read a more abbreviated version of all that. So this is an example of a dependent means t-test in research. All right. Last topic is to return to effect size. So we previously learned effect size for a z-test. Okay, we learned how to calculate a Cohen's d by taking the difference between two means divided by the population standard deviation. We can apply the same formula to a single sample t-test as well as a dependent means t-test. In each case, we're going to use our sample mean as a point estimate of the mean for population 1. Okay, so you can think of population 1 as the treated population. Population 2 is the untreated population. Okay. So with our single sample t-test, we've got our sample mean that we use as a point estimate of a treated population. We've got a comparison value or a known mean for our non-treated population. And then what we need to do is come up with our estimate of population standard deviation using our sample data. Okay. And that the same conventions that we previously learned for small, medium, and large apply. A dependent means t-test, it's the exact same formula. We're just going to use our mean of our change scores. The mean for our comparison population with a dependent means t-test is always 0. And then same thing, we're going to use our estimate of population standard deviation. Okay? So the takeaway here is that whether we're doing a z-test, a single sample t-test, or a dependent means t-test, we're basically calculating effect size in the same way. We're just modifying the formula ever so slightly to reflect whether we're doing a z-test, a single sample t-test, or a dependent means t-test.